Hello YouTube. I've had some requests from my Tesla enthusiast friends to describe my vacuum tube Tesla coil. I'd like to power it on here for you. So that's the vacuum tube Tesla coil, and I'd like to just go over the design of this guy. I built this a few years ago, so I've kind of forgotten some of the details, but I'll try to do the best I can. I started with this book, Vacuum Tube Tesla Coils, so it gives you some ideas and some designs that maybe you could to work with. And I took some lab notes here when I was building this thing, but I've tried to transpose those to a schematic for you. So we'll start. Power comes in via the electric cord. This is 120 volts AC. And so I just have it plugged in here. Comes in to our switch. And this is a microwave oven transformer, high voltage here. And this goes to our microwave oven capacitors. Their total capacitance is 1.5 microfarads. These guys here. You could use one, but I use two just to get a little more power to the Tesla coil. I found it gave a hotter, thicker spark. I got one of these. Be sure you want to get the heaviest duty, most robust diode you can for this. These are found in some of the microwave ovens, but if you have a microwave oven with just a tiny diode, you might want to look online to find a larger diode. Just a final word on the diode. This one is rated at 10 to 16 kV, and they're rated for 1 amp. When this is operating, I've measured a 200 milliamp current that will be flowing through the diode through the vacuum tube. So, but make sure your diode's well rated to handle more than enough voltage and current for the application, so you get a good life expectancy out of it. Next component I'd like to focus on is the low voltage transformer. Now, this was a high voltage microwave oven transformer, but I cut out the windings and I replaced those windings with fewer turns of a very heavily insulated high voltage cable, and I wound that cable until I reached the voltage potential I needed to drive the Triode vacuum tube filament. So this is the power that comes from this transformer is low voltage, and it is used to heat the filament inside the Triode vacuum tube. And again, really important, you want to get high voltage insulation wire to rewind this transformer with. You could probably use a transformer that isn't from a microwave oven. Any transformer would work, but you need the high voltage windings because this filament is going to be at negative 3,000 volts. You want to be sure that this wire won't short out to the transformer, into the main coils, into ground. So, so two transformers to get this coil up and running. One high voltage, one low voltage for the filament of the vacuum tube. Getting the filament the right voltage and current is critical to operate the tube. And I found when I used fewer windings that I couldn't even get the filament hot enough for the tube to function correctly. So yeah, give yourself enough room in your transformer to be able to adjust this value, and try to wind it until you get a value that is comparable for what's called for in the tube's spec sheets. So then you take these, and keep in mind this is 6 volts AC, 3.5 amps AC current. comes down, heats the filament, and the filament is at a negative 3 kilovolts DC. And that drives the tube. Now I'd like to just briefly discuss the operation of the Triode vacuum tube. So what's going to happen, as soon as the power is applied, this filament will heat up. A cloud of electrons is going to be floating around this guy. A high voltage transformer will build up a negative 3 kilovolt potential. Electrons in this cloud are going to want to start moving across the tube through the grid to the plate. So a current will flow. Electrons will flow through the plate into the tank circuit. And as current flows through this coil, it builds up a magnetic field around this coil, which then, in this coil, this is the primary coil that we're looking at here, and that field then induces a current into the feedback coil, which is this finely turned wire here. And you can see that these two coils are magnetically coupled, and when you're building this, it may be critical for you to adjust the amount of turns or the distance to make sure that these are well coupled, because what will happen as that current flows through this coil, expanding magnetic field occurs, cuts the second coil, inducing electrical current in the feedback coil. So then a potential is developed on the grid because the primary coil is inducing current in the feedback coil. The feedback coil puts a potential on the grid, which then shuts off the flow of electric charge. The field relaxes, collapses. Similarly, the potential in this circuit decays. The charge dissipates, and then current can flow again. Flow through the tube, and then the process repeats. So this is an oscillator circuit, and you're pulsing power into the primary tank circuit. It induces electricity in the feedback circuit, which then shuts off the tube. So power's on, feedback shuts it off, turns off, feedback turns off, tube turns on again, and current begins to flow. So you have pulsed current that will be flowing through the tube at the resonant frequency of this circuit, which is approximately 640 kilohertz. And here's one of my old calculations where I plugged in the values of the inductor and the capacitor, and I calculated 649 kilohertz, and then I actually measured it on a scope that had a FFT feature. So my calculator was 649 and my measured was 640 kilohertz. So came pretty close. And I just experimented with different values. I have a 3 nanofarad and a 4 kilo ohm resistor in series with the feedback coil. And I don't think these values were super critical. I just experimented with a couple. You just want to have some resistance and some capacitance on that feedback circuit. And the value for our Tesla coil itself, which is many fine turns of copper wire. They're in the central tube, measured to be 42 ohms and 5.5 millihenries. This was half an ohm, 1.2 millihenries, 500 picofarad, 3 nanofarad, 4 kilo ohms, 1.5 ohms in the feedback coil, 0.13 millihenries inductance for the feedback coil. I did measure the mutual inductance between the primary coil and the secondary coil. I came up with 0.2 millihenries. I didn't measure the mutual inductance between the feedback coil and the primary coil, which might be something worthwhile doing in the future. That's an overview of the vacuum tube coil design. I'd like to give just a few final construction tips on this guy. One thing is, once you wind that feedback coil and you're hooking it up to your tube, these two terminals are the feedback coil, and sometimes when I first started it, it didn't work, and you might have these mixed up. So if you turn it on and first power doesn't produce any effects at the top of the Tesla coil, you may have this feedback circuit backwards. So you may want to just, flip these terminals around. So that's a troubleshooting tip. And if you don't have a cap or a connector for the tube itself, I just kind of with copper wire just kind of did a loop that was the size of this plate terminal, and I soldered a ring of wire around it. I'll just pop this off. It's handy if you can find a socket for your tube. This is an 805 vacuum tube. Yeah, 805s actually. It's written on the glass. And 3 terminals, 2 for the filament, 1 for the grid. And I like to label which terminals are which. This terminal is the filament, the other filament, and this is the grid. I have an F, F, and a G, and that's what the socket looks like. And there's a pin. I just kind of keep in track. I actually have a mark here that tells me which direction this pin on the base of the tube should be facing, and that helps me correctly align the points of contact for the tube and just put it in the socket.